In today's video, we're going to combine two sections, 8.4 and 8.5, and take a look at operations with radical expressions, meaning we're going to add, subtract, multiply, divide, and even look at the rationalizing of the denominators when we need to do that. Not many notes here, just a whole bunch of examples that we're going to blitz through. Feel free to pause and back up if you need to at any point, but we have 6 or 7 examples to go through here, and they'll increase in difficulty. So our first problem here, we have 2 root 20x minus root 45x. And the most important thing you need to get from this section is that you can only add and subtract radicals if they have equivalent radicands. What you really need to think about is you need to treat the radicands, the 20x and the 45x, as if they're variables. For example, I can do 2x minus 1x, that comes out as 1x. You have to have the same thing here, the same radicand, in order to be able to add and subtract these guys. So this is where simplification comes in handy, because we want to simplify some of these guys and see if they can then be combined. 2 root 20x, I'm going to assume here that you have some good experience here with simplifying these radicals. I know that root 20, 20 is 4 times 5. I know the square root of 5. That allows me to make this 4 root 5x minus, same thing here with root 45x. I know that 45 is 9 times 5. 9 is a perfect square. Therefore, I have 3 root 5x. And that's kind of nice because now we have similar radicands and we can now subtract. 4 root 5x minus 3 root 5x, that leaves us with 1 root 5x, which is just the same as root 5x. So pretty easy to do once you get the same radicand. Here's another example, but this time we have some cube roots going on. 2 times the cube root of 16 minus 5 times the cube root of 54. Again, I'm going to speed through it a little bit. I'm going to assume that we're able to simplify these guys a little bit. You have to keep in mind your perfect cubes, 1 cubed, 2 cubed, 3 cubed. If you kind of have them in the back of your head, it makes this a little bit easier. Cube root of 16, I know that 16 is 8 times 2. 8 is a perfect cube that allows a 2 to come out. So I have 4 times the cube root of 2 minus cube root of 54. 54 is 27 times 2. The cube root of 27 is 3. That allows a 3 to come out. So I have now negative 15 cube root of 2. And now I have similar radicands, cube root of 2, cube root of 2. Think of this as 4x minus 15x. That would come out as negative 11x. Same thing here. 4 minus 15 of cube root of 2 leaves me negative 11 cube root of 2. Okay. Moving on to the next one. This time we have one that looks a little messier, and I like this problem because it's going to make a point that you can simplify these guys in a lot of different orders, and as long as you're doing legal, valid steps, as long as you're not breaking any math laws, you're going to get the same answer as the person next to you. So let's see what we can do here. Let's take a look at this one. What I'm looking at first is this fraction here. Can I reduce it in any way? And 75 and 16, there's nothing that goes into both of them, so I'm just kind of stuck here. I need to rewrite it as 2 root 75 over root 16. And then I'm just going to simplify from there. Root 75, I know that 75 is 25 times 3, so therefore I now have 10 root 3. And root 16, that's just 4. So I have 10 root 3 over 4, but wait a minute, I have 10 and 4 here. That's also going to reduce. So I have 5 root 3 over 2. So at least that first piece is done. Let's see what I can do with this second piece. Root 8 over root 32. What I would be tempted to do here is perhaps to try to simplify root 8 and simplify root 32. But there's something else going on here if you kind of look between the lines. I can make this all one fraction. Radical 8 over 32, square root of 8 over 32. And that's nice because 8 over 32 I know is 1/4. And this is going to simplify very nicely. This is root 1 over root 4. And that's just plain old 1/2. So I kind of have all this side work going on. But it gets me to the point that that radical there is just 1/2. So I have 4 times 1/2. I know what 4 times 1/2 is. That's 2. So I have plus 2. So this looks pretty good. If I wanted to make it all one fraction with one denominator, I still have 5 root 3. And now plus 4 because 4 over 2 is the 2. Sometimes we want to write them as one nice little expression rather than 2. But either one is acceptable. Okay, moving on. I'm going to go into multiplying here. You may have thought about multiplying radicals before, but no big worries here. This is just the double distributive property. I'm going to take the 7 and distribute it to both things in the other set of parentheses. So I have 7 root 5 plus 7 root 2. And then I'm going to take my negative root 3 here and multiply it by both of the things in the other set of parentheses here. So I have negative root 15 minus root 6, and unfortunately that's it. There's nothing here that I could add. I don't have anything I can simplify any further. You don't need to write it in any particular order. That's pretty much as good as it's going to get. We would hope that would simplify better, but it's pretty ugly, but there it is. How about this one? So this one I could start thinking about, okay, it's distributive property again. I could take this times this times this, and then root 5, and do my double distributive property. But look between the lines in this problem. Think about what we got here. We have 2 root 3, 2 root 3. Root 5, root 5. We have a plus and a minus. This should really remind you of x plus y times x minus y. And we know that x plus y times x minus y is x squared minus y squared. Well, that still holds here. It's just that our x is worth 2 root 3, and our y is worth negative root 5. So we could use the double distributive property and write out all the terms and simplify them, but if we know that this problem is really just a difference of squares problem, we can go right to this step here. So we know that we can take 2 root 3 and square it, minus negative root 5 and square it. 2 root 3 squared, 2 squared is 4, root 3 squared is 3. I have 12 altogether, minus a negative squared will be a positive, root 5 squared is 5. So I have 5, 12 minus 5 is 7. How about that? So this nasty looking problem here, after we multiply it by using x squared minus y squared, just comes out as 7. Isn't that nice? Okay. Moving on in our journey here. Now we get to rationalizing denominators. One of our rules was that we cannot have, there's two things going on here. First of all, we're not supposed to be able to have a fraction inside the radical. And we're also going to have something here where we have to rationalize the denominator. So let's see what's happening here. I'm going to split this up. I have this opposite sign just kind of hanging out here. I have root 50m to the 4th over root p to the 5th. I'm going to deal with the top and the bottom separately, numerator, denominator. 50m to the 4th, that is 5m squared, root 2. P to the 5th, that is p squared, root p. Doesn't look like the best thing in the world. I am not allowed to have a radical denominator. We are not simplified if we have a radical in the denominator. So the technique is that we multiply the numerator and denominator by root p. Keep in mind that this step is valid because root p over root p, or anything divided by itself for that matter, is worth 1. And multiplying by 1 doesn't affect the value of our fraction. So what happens when we do that? Well, in the numerator, I have 5m squared root 2p. And in the denominator, I now have p cubed. One small thing about this one, you do have to pay attention here. P cubed you have to be careful of, because what if my p was negative? This is one of those situations where I need to have my absolute value bars. When I was over here before, p squared, I don't have to worry about the absolute value bars because p squared was going to come out positive anyway. But this time I do need it because of an odd power there. So I have to account for the fact that p could be a negative number here. One small little thing there. How about this guy? Cube root. All right, we'll continue doing the same thing here. We're going to break up the top and the bottom. Cube root of 27 over cube root of 16. Cube root of 27, that's oh so nice. We know that that is 3. Cube root of 16, 16 is 8 times 2. So I have 2 times the cube root of 2. I'm going to bring that down here because I want to talk about this a little bit more. 3 times 2 times the cube root of 2. I need to rationalize the denominator, but you really need to think about this one. If I were to take the numerator and denominator and multiply them by cube root of 2 here, think about what that would do, especially in the denominator here. The cube root of 2 times the cube root of 2 is the cube root of 4. Well, the cube root of 4 would not allow this to simplify. I need the cube root of 8. So this is going to be our trickiest one here. I'm actually going to multiply the top and the bottom by the cube root of 4. The reason being, when I take cube root of 2 times the cube root of 4, that will give me the cube root of 8. I need a perfect cube here in order to have the radical be eliminated. So let's follow this along here. I will have 3 times the cube root of 4 times over 2 times the cube root of 8. And a cube root of 8, I know, that's worth 2. So 3 times the cube root of 4 over 4. So when we have cube roots, and we're not going to go much beyond cube roots, we're going to have these special cases here we really have to think about. So this might be one we have to work on in class tomorrow. Kind of circle it and put stars next to it if you have questions. And to end this video, I'm going to leave you with this one, food for thought. This is not simplified. It has a radical denominator. So I'm going to challenge you to think about what would it take to simplify this one, and we'll talk about it in class tomorrow.